Ever wondered what drives the speed of chemical reactions? Well, you're about to find out. Welcome to the world of chemical kinetics, the study of rates at which chemical processes occur. It's like the heartbeat of chemistry, dictating the pace at which changes happen. Today, we're going to explore some key components of this fascinating field. We'll start with the order of reaction, which is like a rule book defining how the concentration of reactants influences the speed of a reaction. Then we'll dive into the effect of temperature, because let's face it, whether we're baking a cake or brewing a potion, temperature matters. Next, we'll unravel the mysteries of the Arrhenius equation and activation energy. We'll also touch upon degradation pathways and the aspects of physical and chemical instability. Lastly, we'll peek into accelerated stability studies and see how they help us predict the shelf life of medicines. Get ready to dive into the fascinating world of chemical kinetics. What determines the speed of a chemical reaction? Let's start with the order of reaction. In the world of chemistry, the order of a reaction refers to the power to which the concentration of a reactant is raised in the rate equation. It's a vital concept that helps us determine how the rate of a reaction changes as the concentrations of the reactants change. Now, you might be wondering, how do we determine the order of a reaction? Well, it's not always as straightforward as you might think. It's not determined by the stoichiometric coefficients in the balanced chemical equation, but rather it's determined experimentally. Imagine you're conducting an experiment. You would change the concentration of one reactant while holding the others constant, then measure how the rate of reaction changes. If the rate doubles when the concentration doubles, the reaction is first order with respect to that reactant. If the rate quadruples when the concentration doubles, it's second order. If the rate doesn't change when the concentration changes, it's zero order. But why is the order of reaction so important? Well, knowing the order of a reaction can help us predict how the rate of reaction will change under different conditions. This is particularly useful in industrial settings where understanding the reaction rate is crucial for optimizing production processes. For instance, if a reaction is first order, we know that increasing the concentration of a reactant will increase the reaction rate. On the other hand, for a zero-order reaction, changing the concentration of the reactant doesn't affect the rate. It's like having a roadmap for a journey. The order of reaction gives us a route, a direction to understand how changes in reactant concentration affect the speed of a chemical reaction. So remember, the order of reaction is not just a number, it's a key to understanding the dynamics of a chemical reaction, a tool to predict reaction rates, and a guide to optimizing chemical processes. Knowing the order of a reaction, we can predict how a reaction's rate will change under different conditions. Ever noticed how some reactions speed up when heated? Let's find out why. Picture this: a crowded dance floor. The dancers are molecules, and their bumps and collisions are the chemical reactions. When the DJ turns up the heat, the dancers move faster, collide more often, and with greater energy. This is what happens in a chemical reaction when you increase the temperature. Now let's meet our DJ, Svante Arrhenius. He gave us an equation that lets us quantify the temperature's effect on reaction rates. This equation ties together the rate of reaction, the activation energy. That's the energy needed to start the reaction, and temperature. It's a bit like our DJ's control panel adjusting the tempo on the dance floor. So as you can see, temperature has a significant role in the speed of chemical reactions. But how do we measure this effect exactly? Stay tuned to find out. What's the math behind the temperature effect? Enter the Arrhenius equation. Now, if you've ever wondered how scientists quantify the effect of temperature on reaction rates, the Arrhenius equation is your answer. Named after the Swedish chemist Svante Arrhenius, this equation is a mathematical representation of how reaction rates speed up as temperatures rise. Let's break it down. The Arrhenius equation is written as K equals A times E to the power of negative E sub A over R times T. Here, K is the rate constant, A is the frequency factor, E sub A is the activation energy, R is the universal gas constant, and T is the temperature in Kelvin. The frequency factor, A, represents the number of attempts per unit time that molecules make to react together. It's like the number of times two people try to high-five each other in a minute. Now, let's focus on the star of the show, the activation energy, E sub A. This is the energy barrier that needs to be overcome for a reaction to occur. Imagine a ball at the bottom of a hill. It needs a certain amount of energy to roll up and over the hill. That's exactly what activation energy is in a chemical reaction, the energy needed to get the reaction going. Did you notice the negative sign in front of the E sub A in the equation? This means that as the activation energy increases, the reaction rate decreases. The higher the hill, the harder it is for the ball to roll over, right? And how does temperature come into play? As temperature increases, more molecules have the energy to overcome the activation energy barrier, and hence, the reaction rate increases. In essence, the Arrhenius equation gives us a way to calculate and understand how much energy is required to initiate a reaction and how temperature influences this. It's like having a secret key to unlock the mysteries of chemical reactions. With the Arrhenius equation, we can calculate how much energy is needed to kickstart a reaction. But what happens when things don't go as planned in a reaction? Let's delve into the realm of degradation, pathways, and instability. Think of a degradation pathway as a detour on your journey from reactants to products. Instead of smoothly transitioning from point A to point B, your reactants might take an unexpected turn and end up somewhere else entirely. Physical instability is one such detour. It's when the physical properties of a substance change, like when a crystal dissolves or an emulsion separates. This can drastically affect the outcome of a reaction. Imagine if you're baking a cake and your sugar suddenly decides to crystallize. That's not going to make for a very tasty dessert, is it? Chemical instability, on the other hand, is a bit trickier. It's when the chemical structure of your reactants changes. Your reactants might decompose, react with impurities, or experience other chemical changes that prevent them from becoming the products you want. Going back to our baking analogy, it's as if your flour suddenly turned into yeast. That's going to cause some serious issues with your cake. These degradation pathways can be influenced by a variety of factors, including temperature, pH, and light. For instance, certain medications degrade when exposed to light, hence why they are stored in dark bottles. Similarly, some reactions only occur at specific pH levels or temperatures. The unpredictability of chemical reactions can make them seem almost magical, but there's no wizardry here, just science. By understanding degradation pathways and instability, we can anticipate these changes and take steps to prevent them. We might adjust the pH, alter the temperature, or add stabilizers to keep our reaction on track. In the grand scheme of things, these unexpected detours and changes are part of what makes chemistry so fascinating. They remind us that while we can influence chemical reactions, we can't always control them. Chemical reactions can be unpredictable, but understanding degradation pathways and instability helps us anticipate and control these changes. How can we predict the long-term behavior of a chemical substance? Let's talk about accelerated stability studies. These studies are like a crystal ball for chemists. They enable us to forecast the future stability of a substance by subjecting it to conditions more severe than it would typically experience. Imagine you're baking cookies. You want to know how they'll taste tomorrow, but you don't want to wait a day. So you bake a batch at a higher temperature to speed up the process. That's essentially what accelerated stability studies do. By exposing a substance to increased temperatures, humidity, or light, we can observe changes in its physical and chemical properties. This allows us to predict its behavior under normal conditions over time. These studies are crucial in industries like pharmaceuticals, where understanding the long-term stability of a drug can be a matter of life and death. Accelerated stability studies allow us to predict the future, at least when it comes to chemical substances. Chemical kinetics might seem complex, but it's the key to understanding how reactions work. We've journeyed together through the fascinating world of chemical kinetics. We've discovered the order of reactions, how temperature can influence the rate, and the significance of the Arrhenius equation and activation energy. We've delved into the mysteries of degradation pathways and the factors that contribute to physical and chemical instability. And we've learned how accelerated stability studies can provide valuable insights into a substance's long-term behavior. This knowledge, my friends, is not just theoretical. It's the bedrock for numerous practical applications, from drug formulation to environmental science. It's a testament to the beauty and complexity of the world we live in, seen through the lens of chemistry. So don't stop here. Let's continue our journey together. Subscribe for more because you won't find me later. Keep exploring the fascinating world of chemistry with us.